Hi everyone, I'm Aksa. I'm a PhD student at CMU and I'm going to present our work on protecting smart homes from unintended application actions. This is a collaborative work with my advisors Vyas Sekar and Yuvraj Agarwal. So we all know the hype around IoT devices and smart homes. Let's try to make a smart home. Consider a user who goes to Home Depot and gets a few smart home devices. The user configures these devices on their phone by downloading apps to control these devices. After setting up everything and configuring a few automations, the user hopes that everything will work fine. A few moments later, the house of the user is on fire. This is because of an interaction between two apps. The first app closes the water supply, turns the water supply off when a leak is detected, and the second app tries to turn water sprinklers on when there is smoke. Now, if the first app is triggered before the second app, then water sprinklers will not be able to turn on because the water supply is off. This is an example of an unintended inter-app interaction that the user didn't think of. In fact, smart apps can cause many unintended actions because of two reasons. The first one is inter-app interaction, as we observed here, and the second one is user misconfiguration. For example, consider the app which locks an unlocked door after X minutes. If the user wrongly configures this X value to say 10 minutes, the door will remain open for too long. That may allow an intruder to enter the house. Hence, in this work, we try to verify if a set of apps deployed in a smart home satisfies certain safety intents. Examples of these intent violations can be apps having conflicting actions. This task is non-trivial because of two reasons. The first challenge is that state-of-the-art smart apps are complex. Let's deep dive into what I mean by complex. Let me give an example of a Samsung SmartThings app. Let's consider the same app which detects if leak is detected for time duration and then turns the water valve off. The app takes a water sensor as input. It has an input duration D, and it operates on water valve. The water sensor and valve are devices, and duration is a user configurable input. Next, since smart apps are event-driven programs, the app subscribes to an event from the water sensor. When this event is received, a water handler function is called. You don't need to understand the logic here. On a high level, this handler function checks if leak is detected for time duration, and then it triggers the function func. The state.wet here is a persistent global variable to keep state in the app. And run in here is a timed API which waits for D duration and then calls the function func. The function func basically checks if the state is still wet, and then it turns the water valve off, which here is a device action. So smart apps have user configurable inputs, state, and time. In this work, we argue that modeling time, state, and user input is necessary to detect safety violations. For example, consider the same app which waits X minute before locking an unlocked door. Here, if we do not model the wait part, the door is locked after being unlocked, resulting in no violation. To reason about the value of wait, we need to model time in an app to say which values of X are safe. Prior work such as SIFT, Sorteria, etc. do not model time, and hence they cannot find this violation. Similarly, consider the same app. Now here, if we do not check for different values of X, we will not be able to reason about and guide the user regarding what values of X are safe. Prior work does not reason about safe configurations, and hence they cannot guide about what values of X will be safe here. Similarly, the next challenge is that there can be direct and indirect inter-app interactions that may lead to safety violations. For example, consider this indirect interaction between apps The first app which again detects a leak and then turns water supply off, and the second app which detects smoke and then tries to turn water sprinklers on. This is an example of a blocked action which can have disastrous consequences. So in this paper, we argue that in addition to modeling state, time, and user inputs within an app, we also need to model the inter-app interactions. These interactions can be direct, for example, apps causing conflicting actions on the same device, or indirect. For example, to find this violation which results from an indirect interaction between apps, we need to model the interaction between water supply and water sprinkler. And if we don't do that, then we will not be able to detect this violation. In fact, prior work actually doesn't model indirect inter-app interactions and hence will miss this violation. To summarize, none of the prior work handles user inputs, state, time, and environment interactions altogether. It is because they consider less expressive abstractions for an app, which does not allow them to model certain app features. For example, Swift cannot model apps which have timed APIs or apps which are stateful. Prior work also doesn't model the indirect inter-app interactions. To this end, we propose PSA, which is a static analysis model checking based tool. PSA takes the source code of apps deployed in a smart home as input. A platform-dependent parser in PSA then creates app models for our chosen abstraction and feeds them into a model generator. The model generator also takes intents selected by the user and a device environment library as input. The model generator looks at the sensors used in the app and the actuators that the app actuates on and creates the relevant models. These models are fed into an off-the-shelf checker, which then checks if the model satisfies safety intents. Finally, PSA outputs counterexample and a set of safe configurations for the apps. Now let's look at the app abstraction part, which basically handles the challenge 1, which was that smart apps are complex. PSA uses timed automata to model apps. For the app source code, the parser, which is specific for a given smart home platform, will convert app code to timed automata models. We choose timed automata as an abstraction because it is expressive enough to model time, state, and user configurable inputs in an app. At a high level, a timed automata extends a finite state machine with real-valued clock variables. As an example, consider the same app which turns water supply off if leak is detected for D duration. Initially, the app waits for events from the water sensor. After receiving an event, it checks if the value is wet. This conditional on a transition is called a guard, which specifies that the transition can only be taken if this condition is satisfied. If the sensor value is wet, then it maintains global state of wet. After this, we need to wait for D duration and then turn valve off if sensor state is still wet. To do this, we use a clock variable to keep track of time. This is done by adding an invariant on S2. This states that I can stay at S2 for at most D duration. First, we reset the clock because we want to track time since this time, and then wait at S2 for D duration. After D duration has passed, we check if the state is still wet and then turn the water valve off and return to the initial state. I omit some transitions here to simplify the model. At a high level, we model events and actions using the time automata construct of synchronization labels, which synchronize different automata. The synchronization label for event will synchronize with sensor model. We model sensor values using discrete variables. Clock is modeled using the clock variables, and discrete state is modeled using discrete variables. Finally, user inputs are modeled using parameters. Please refer to the paper for more detail on this. Hence, to summarize, for the first challenge of complex smart apps, PSA chooses timed automata as a suitable abstraction to model the time, stateful, and user configurable nature of smart apps. This transformation from app to timed automata is non-trivial. Please refer to the paper for details. After we have figured out the abstraction for apps, now let's consider the model generator. The model generator creates relevant environment, sensor, and actuator models for an app. These models are necessary to capture inter-app interactions. This part of PSA concerns the second challenge, which is inter-app interactions. There can be indirect interactions between apps. For example, these two apps indirectly interact through a common environment attribute, water supply. To model this interaction, PSA separately models water valve, sprinklers, and the environment attribute, water supply. To conclude, PSA models sensors, actuators, and environment attributes in addition to apps to capture inter-app interactions. To see how we actually model these smart home components, please refer to the paper. Hence, for challenge 2, PSA separately models each component of a smart home to capture all of their direct and indirect interactions. Finally, for PSA output, consider this again auto lock door app. Here, PSA will output a set of safe configurations, which in this case would be that X should be at most 1 minute. We evaluate PSA on Samsung SmartThings, which is the state-of-the-art smart home framework. PSA is also applicable to other platforms such as IFTTT, Zapier, Apple HomeKit, etc. We evaluate on 86 Samsung SmartThings apps. 21% of these are stateful, 43 are timed, and 59% have user inputs. In total, we find 640 violations. Some of these violations are particularly dangerous. For example, the following violation results in carbon dioxide vent being turned off when CO2 levels are high. We find 19 new violations which none of the prior work finds. For example, in one interaction, lights are turned on and off so frequently that it causes a strobing effect. We compare PSA with two baselines to demonstrate the importance of modeling state, time, and user inputs. These baselines are approximation of SIFT and Soteria. In terms of false positives, baselines can have up to 35% false positives. Please refer to the paper for details about these intent violations. To summarize, PSA is a model checking tool which verifies smart home deployments for safety violations. PSA uses timed automata to model apps, and PSA models each smart home component separately to capture inter-app interactions. PSA finds 19 new violations that no prior work finds. Thank you.